Right, well, believe it or not, you actually now know enough Lisp to write essentially any numerical procedure that you'd write in a language like Fortran or BASIC or whatever, or essentially any other language. You're probably saying that's not believable, right? Because you know that these languages have things like for statements and do, until, while, or something. But we don't really need any of that. In fact, we're not going to use any of that in this course. Let me show you by, again, looking back at square root. Let's go back to this square root algorithm of Heron of Alexandria. Remember what that said? It said to find an approximation to the square root of x. You make a guess. You improve that guess by averaging the guess and x over the guess. You keep improving that until the guess is good enough. I already alluded to the idea. The idea is that if the initial guess that you took, if that initial guess was actually equal to the square root of x, then g here would be equal to x over g. So if you hit the square root, averaging them wouldn't change it. If the g that you picked was larger than the square root of x, then x over g will be smaller than the square root of x, so that when you average g and x over g, you get something in between. Right? So if you pick a g that's too small, your answer will be too large. If you pick a g that's too large, if your g is larger than the square root of x, then x over g will be smaller than the square root of x. So averaging always gives you something in between, and then it's not quite trivial, but it's possible to show that, in fact, if g misses the square root of x by a little bit, the average of g and x over g will actually keep getting closer to the square root of x. So if you keep doing this enough, you'll eventually get as close as you want. And then there's another fact, that you can always start out this process by using 1 as an initial guess. And it'll always converge to the square root of x. Right, so that's this method of successive averaging due to Heron of Alexandria. Let's write it in Lisp. Well, the central idea is, what does it mean to try a guess for the square root of x? Okay, so let's write that. So we'll say, define to try a guess for the square root of x. What do? We'll say if the guess is good enough, the guess is good enough to be a guess for the square root of x, then as an answer we'll take the guess. Otherwise, we will try the improved guess. We'll improve that guess for the square root of x, and we'll try that as a guess for the square root of x. We'll close the try, close the if, close the define. So that's how we try a guess. And then the next part of the process said, in order to compute square roots, we'll say define to compute the square root of x. We will try 1 as a guess for the square root of x. Well, we have to define a couple more things. We have to say, how is a guess good enough, and how do we improve a guess? So let's look at that. The algorithm to improve a guess, right, to improve a guess for the square root of x, we average, that was the algorithm, we average the guess with the quotient of dividing x by the guess. Right, that's how we improve a guess. And to tell whether a guess is good enough, well, we have to decide something. This is supposed to be a guess for the square root of x, so one possible thing you can do is say, when you take that guess and square it, do you get something very close to x? For example, so one way to say that is to say, I square the guess, subtract x from that, and see if the absolute value of that whole thing is less than some small number, which depends on my purposes. Right? Okay, so there's there's a complete procedure for how to compute the square root of x. Let's look at the structure of that a little bit. Right? I have the whole thing. I have the notion of how to compute a square root. That's some kind of module, right? That's some kind of black box. It's defined in terms of, right? It's defined in terms of how to try a guess for the square root of x. Try is defined in terms of, well, telling whether something's good enough and telling how to improve something. So good enough. Try is defined in terms of good enough and improve. And let's see, what else do I fill in? Well, you all go down this tree. Good enough was defined in terms of absolute value and square. And improve was defined in terms of something called averaging, and then some other primitive operator. So try, square root is defined in terms of try. Try is defined in terms of good enough and improve, but also try itself. So try is also defined in terms of how to try itself. Well, that may give you some problem, right? Your high school geometry teacher probably told you that it's naughty to try and define things in terms of themselves, because it doesn't make sense. But that's false. Right? Sometimes it makes perfect sense to define things in terms of themselves, and this is a case. And we can look at that. We can write down what this means. We say, suppose I ask Lisp what the square root of 2 is. Well, what's the square root of 2 mean? Well, that means I try 1 as a guess for the square root of 2. Right, now I look, I say, gee, is 1 a good enough guess for the square root of 2? And that depends on the test that good enough does. And in this case, good enough will say, no, 1 is not a good enough guess for the square root of 2. So that'll reduce to saying I have to try the improve 1 as a guess for the square root of 2, and try that as a guess for the square root of 2. Improving 1 as a guess for the square root of 2 means I average 1 and 2 divided by 1. Right, so this is going to be the average. This piece here will be the average of 1 and the quotient of 2 by 1. Right, so that's this piece here. And I'm going to try, right, and this is 1.5. So this square root of 2 reduces to trying 1 for the square root of 2, which reduces to trying 1.5 as a guess for the square root of 2. Right? So that makes sense. Let's look at the rest of the process. Here, if I try 1.5, right, that reduces. 1.5 turns out to be not good enough as a guess for the square root of 2. So that reduces to trying the average of 1.5 and 2 divided by 1.5 as a guess for the square root of 2. That average turns out to be 1.333. So this whole thing reduces to trying 1.333 as a guess for the square root of 2, and then so on. Right? That reduces to another called a good enough, 1.4 something or other, and then it keeps going until the process finally stops with something that good enough thinks is good enough, which in this case is 1.4142 something or other. Right? So the process makes perfect sense. This, by the way, is called a recursive definition. And the ability to make recursive definitions is a source of incredible power. And as you can already see, I've hinted at, it's the thing that effectively allows you to do these infinite computations that go on until something is true, right, without having any other constructs other than the ability to call a procedure. Well, let's see, there's one more thing Let me show you a variant of this definition of square root here on the slide. Here's a sort of the same thing. What I've done here is packaged the definitions of improve and good enough and try inside square root. So in effect, what I've done is I've built a square root box. So I built a box that's this square root procedure that someone can use. They might put in 36 and get out 6. And then packaged inside this box are the definitions of try and good enough and improve. Right, so they're hidden inside this box. And the reason for doing that is that if someone's using this square root, if George is using the square root, George probably doesn't care very much that when I implemented square root, I had things inside there called try and good enough and improve. And in fact, Harry might have a cube root procedure that has try and good enough and improve. And in order to not get the whole system confused, it would be good for Harry to package his internal procedures inside his cube root procedure. Anyway, this is called block structure, this particular way of packaging internals inside of a definition. And let's go back and look at the slide again. The way to read this kind of procedure is to say, to define square root, well, inside that definition, I'll have the definition of an improve, and the definition of good enough, and the definition of try, and then subject to those definitions, the way I do square root is to try 1. And notice here I don't have to say 1 as a guess for the square root of x, because since it's all inside this square root, it sort of has this x known. Okay, well, let me summarize. We started out with the idea that what we're going to be doing is expressing imperative knowledge. And in fact, here's a slide that summarizes the way we looked at Lisp. We started out by looking at some primitive elements, and addition and multiplication, some predicates for testing whether something's less than or something's equal. And in fact, we saw really sneakily in the system we're actually using, these aren't actually primitives, but it doesn't matter. What matters is we're going to use them as if they're primitives. We're not going to look inside. And we also have some primitive data, like some numbers. We saw some means of composition, means of combination, the basic one being composing functions and building combinations with operators and operands. And there were some other things like cond and if and define. But the main thing about define in particular was that it was the means of abstraction. It was the way that we named things. You can also see from this slide not only where we've been, but holes we have to fill in. At some point, we'll have to talk about how you combine primitive data to get compound data, and how you abstract data. So you can use large globs of data as if they were primitive. So that's where we're going. But before we do that, for the next couple of lectures, we're going to be talking about, first of all, how it is that you make a link between these procedures we write and the processes that happen in the machine, and then how it is that you start using the power of Lisp to talk not only about these individual little computations, but about general conventional methods of doing things. Okay, are there any questions?
Yes.
No.
If we defined A using parentheses instead of as we did, what would be the difference?
If I wrote this, if I wrote that, what I would be doing is defining a procedure named A, in this case a procedure of no arguments, which when I ran it would give me back 5 times 5.
Right. I mean, you come up with the same thing except for you really got a different
Right, and the difference would be in the old one. Let me be a little bit clearer here. Let's call this A, like here, and pretend here, just for contrast, I wrote define D to be the product of 5 and 5. And the difference between those, let's think about interactions with the Lisp interpreter. I could type in A, and Lisp would return 25. I could type in D. If I just typed in D, Lisp would return compound procedure D. Because that's what it is. It's a procedure. I could run D. I could say, what's the value of running D? Here is a combination with no operands. And I see there are no operands. I didn't put any after D. And it would say, oh, that's 25. Or I could say, just for completeness, if I typed in, what's the value of running A, I get an error. And the error would be the same one as over there. The error would say, sorry, 25, which is the value of A, is not an operator that I can apply to something.